Hello learners, welcome again on another class in digital system design, and the topic of today's lecture is magnitude comparator circuit design. Have you come ever across that how digital circuits compare two numbers? How the comparison operation can be easily implemented with the help of simple logic gates? We shall try to answer these questions in today's class. So let us begin. So magnitude comparator is a combinational logic circuit which compares two numbers, say A and B, and determines their relative magnitudes. The output may be, say, A is greater than B, A less than B, or A is equal to B. So these are the three possible outcomes after comparison of the two numbers. So let us begin to understand simple logic behind this 1-bit magnitude comparator. Suppose I take 1-bit magnitude comparator A and B. Inputs are A0 and B0, and here we write outputs may be A is greater than B, or A less than B, or finally A is equal to B. So 1-bit magnitude comparator, there may be four possible inputs. First is 0, 0. In this case, the output will be logic 1 for the case A is equal to B. Whereas for the case A is greater than B will be 0, A is less than B will be 0. Similarly, another case for input is 0, 1. In this case, we can see A0 is 0 and B0 is 1. So obviously, B0 is greater than A0. That is why where A is less than B will be logic 1, whereas A is greater than B logic 0 and A is equal to B logic 0. Next case is 1, 0. For this case, A is greater than B will be logic 1 and rest logic 0. And for last case, that is 1, 1, when both A0 and B0 are 1, 1. In that case, again, A is equal to B and rest are 0. So these are the all four possible input condition for 1-bit magnitude comparator. Now, how to design circuit? For that purpose, we have to express these outputs in terms of Boolean expressions. So for A is greater than B, for this case, the Boolean expression in soft form can be taken from the case when A is greater than B. So that is A0, B0 bar. And for the case of A is less than B, at that here we have logic 1. So this is the case when A0 bar, B0. And finally, the case when A is equal to B, for that we have to write the Boolean expression. So we have two expressions where A is equal to B are here when A bar, B bar, and A, B. So A0 bar, B0 bar plus A0, B0. Now, just observe that for implementing A is greater than B, we can use simple logic gates and of A0, B0 bar. And for A less than B, again we can use some simple logic gates where A0 bar, B0 and of this. Whereas for A is equal to B, for that purpose we can use a logic gate called exclusive NOR gate or X NOR gate. Let me explain you why. If we see the truth table of exclusive OR gate, XOR gate, suppose A, B are input and Y is the output. So for that 0 0 exclusive NOR here 1, then 0 0 1 will be X NOR, 0 1 will be 0, 1 0 will be 0 and 1 1 will be 1. So here you can see when inputs are 0 0 or 1 1 means both are equal, then in the exclusive NOR gate outputs are 1. That is why this equality condition can be easily implemented with the help of exclusive NOR gate. So let us try to implement. So we can write here say A0, then here we will get A0 bar and B0 bar, and for A is greater than B we have expression A0 and B0, and of A0 and B0, this is A greater than B, whereas for B greater than A is written as, this is A less than B, and third case when both are equal with the help of exclusive NOR gate. So this will give you A is equal to B. In this way we can easily implement one bit magnitude comparator. So we have seen if one bit is there, then there are 4 possible combinations and 2 inputs combination and 2 inputs. If there are 2-bit magnitude comparator, if we have to design 2-bit magnitude comparator, then there will be 2 into n, that is 4 inputs, and 2 to power 2n, that much will be input combinations. Similarly, if we have 3-bit magnitude comparator, then we will have 6 inputs and 2 to power 6, 32 number of possible combinations, which becomes unmanageable. So we use an algorithm or some after observing there is a some repeated pattern. Based on that, we can design magnitude comparator circuit for any number of input. So let us see how it is going on. For that, let us take two numbers. Take two numbers with 4 bits. So A is equal to, I'm writing A3, that is most significant bit, then A2, A1, A0. This is the first number. Similarly, second number, which is B, and their most significant to least significance are B3, B2, B1, and B0. These are the two numbers. And we can take any numbers also if we wish. Suppose 1, 0, 1, 0, 1, 1, 0, 1, something like that. Now for equality condition, say for equality condition, that is number A is equal to B. When we can conclude that these two numbers A and B, which are here 4 bits, are equal. So let us see the pattern. A is equal to B if and if only A3 is equal to B3, this most significant bits. Then A2 is equal to B2. A1 has to is equal to B1 and A0 has to is equal to B0. It means if it is 1 0 1 0, then B has to be also 1 0 1 0. Then only equality condition can be satisfied. Each bits starting from most significant bit. We compare like that. If any most significant bit is uh, greater than the earlier one, then whichever is the greater will conclude is greater irrespective of other bits. Okay, so even we can take here example like suppose 1 0 1 0 and I take 0 1 1 1, that is the number A and this is the number B. Here if we start comparing this most significant bit, so A3 is greater than the B3. So from here only we can conclude that A is greater than B without comparing next lower bits like A2, A1 or A0 with B2, B1 and B0. And that is what we do in practical life. So that is the case for equality. Now, how to implement with the help of logic gates? Just we have seen that equality condition can be implemented with the help of exclusive NOR gate. So I will write now algorithm, say xi is equal to ai bi plus ai bar bi bar, where I is equal to 0, 1, 2, 3 for the case of 4 bits. So I xi is equal to 1 when both pairs of bits, when both pairs of bits are either 0 or 1. This is the case we have seen here in exclusive OR. So this is 1 when either both are 0, 0 or both are 1, 1. So for each bit, so A is equal to B, it means X3 means comparing A3, B3, both are equal, then we can write X3. Then AND operation with X2, AND operation with X1, and operation with X0. Then only we can say that number A is equal to number B having 4 bit each. So by implementing X3 with the help of exclusive NOR gate, then A3 with exclusive NOR gate, A1 exclusive NOR gate, and A0 exclusive NOR gate, then these bits will come, and with the help of AND operation of these 4 outputs will give you the equal condition of output. Now let us write for the case. This is the case 1 and this is the case 2. I wanted to write for A is greater than B, first one. So A is greater than B can be possible only if A3 and B3 bar means 1 0, that is the most significant bit is 1 0. If this is not the case, then it means that information is captured by X3. The next lower bit of the numbers shall be compared. That is the A2 B2 bar. It has to be 0 and A2 has to be 1. Then only we can decide that A is greater than B. Even if this is not the case, then we go for comparing lower bits, provided that these previous two cases has to be considered, like X3 then X2. Then we have A1 B1 bar means third lower bits are being compared. Then only we can say A is greater than B. Even at this case also your bits are equal. Then we compare for last bit, provided that you capture the information of previous 3 bits equal condition, like X3, X2, X1. Then last condition has to be greater than, then only this condition will be satisfied that A is greater than B. So let us write. So A0, B0 bar. So now we have completed the Boolean expression for the case of A is greater than B. So this is the Boolean expression of A is greater than B. Now case 3. And case 3 is A is less than B or B is greater than A. Both are same. Let us write the Boolean expression for this case when A is less than B. So for that case, again similar condition, A3 bar B3. When A3 is 0, B3 is 1, then we can say that B is greater than A. If this is not the case, it means A3 and B3 both are same, that is captured by X3. Then we write A2 bar B2. Then only we can say B is greater than A or A is less than B. Even these two bits are equal, Then we compare third bit, provided that we capture this information through x3, x2, and then a1 bar b1. Then only we can say b is greater than a. And lastly, last bit comes when all three higher bits are equal. It means x3, x2, x1, then a0 bar b0. So this last bit has to be greater in case of b is greater than a. Then here it is b0. So now we got all three output expression for all three outputs. So we have seen that for equal condition, say this case 1 means a is equal to b. For that we have seen x3, x2, x1, x0. Case 2, a is greater than b. For that purpose, what is the Boolean expression? Let us write here. A3 B3 bar plus X3 A2 B2 bar. Provide for this case A is greater than B plus X3 X2 A1 B1 bar plus X3 X2 X1 then A0 B0 bar. Now case 3, A is less than B. For that we have to write A3 bar B3 most significant bit. If this is not, if these are equal, then we go for next lower bit comparison x3, then a2 bar b2 plus x3 x2 a1 bar b1 plus x3 x2 x1 a0 bar b0. Just reverse of a is greater than b will be a is greater than a is less than b. Now in order to implement we need lines, that signal lines. So let us take signal lines here. So this will be suppose a a0, then we can take a1 a2 a3 and here b0 b1 b2 b3 and after that let us write then this is suppose a3 a2 a1 a0 and b3 b2 b1 b0 and after that let us implement. So let us implement with the help of some different color. So I will implement first equality condition x0. So x0, or no, first let us see x3, because we start comparing with most significant bit. So I take x3 and b3, a3 and b3, put into exclusive NOR, and this will give you for x3, then x2, then a2, b2, then this is x2, then next is a1, b1, this will give condition for x1, then x0 will be achieved by taking exclusive OR of a0, b0. And in order to get the output, I simply combine with AND gate. This gives the condition for, if this is 1, it means both numbers are equal. Now let us implement for A is greater than B. Take another color. So if I take A is greater than B, it means A3 B3 bar. A3 is here, A3, and B3 is here. Put not gate, and this will be AND operation. This will be A3 B3 bar. If this is not equal, then we have to take the from x3. This is x3. Now from here we can take x3, one input, x3, then a2 is here, and b2 bar. B2 is here. We put NOT gate, then this is b2, and after that this has to be AND operation, and then we can get, this is the case when x3 a2 b2 bar is the case, and here this is a3 b3 bar. These two are there. Now third case, it means we have to take x3. Let me use another pen. This one. So I take x3 from here only. Then x2 I can take from, there is a problem, x2 is here, x2, then x1 for for third bit comparison will be A1 and B1 bar. B1 and put here not gate. And then AND gate. So this case is giving you X3, X2, A1, B1 bar. This is the case. Now for last one, let me extend this line because this line is becoming shorter. We are implementing the 4-bit magnitude comparator circuit. Now, last bit means least significant bit expression. So for that purpose, we have this comes situation when you have all other higher bits are equal. It means that x3, let me take this red color. It means x3 is 1, then x2 we have logic 1, and then x1 which is here is also equal. Then only the situation comes last one. Now last bit is here A0. A0 has to be 1, this one. And B0 has to be bar. So B0 bar. Now these output will become the input of AND gate. Now we have all outputs here. Put OR gate. Sorry, it should not be misrepresented. So this is OR gate. And you will get here A is greater than B. Interesting thing is that A is less than B can be easily taken as output, just putting NOT gate of A is greater than B. Because when A is not because A is greater than B, put the NOT gate, then A will be less than B. So in this way, no need to implement the Boolean expression for A is less than B. This one. Only two are essential. First one is A is equal to B, and second one is that A is greater than B. Third expression you can easily get by taking the inverse of A is greater than B. Then you will get the A is less than B. So in this way, in today's class, we have learned how to design 4-bit magnitude comparator. We started knowing that how 1-bit magnitude comparator can be designed. Then later on we appreciated that when number of bits increases, the complexity increases also, because the table where entries are there for all possible combinations are unmanageable. Then we apply some algorithm where we have seen that there is some repeated mechanism, repeated patterns in the input conditions and then getting the output. From there, we, we, we could apply an algorithm which captures the repeated pattern So three conditions: A is equal to B, A is greater than B, or A is less than B. And there we wrote the expressions, Boolean expressions, which captures all three possible output combinations, like A is greater than B, A is greater than B, E is less than B, or A is equal to B. And A is equal to B can be easily implemented with the help of exclusive NOR gate. And these outputs are further used while implementing the other Boolean expression for the case of A is greater than B. And A is less than B can be easily implemented by taking just inverse of A is greater than B. We can get the A less than B output condition. So in this way, we can design a circuit that is called magnitude comparator. I have created another video in which you can experimentally do this comparison operation. So I will give that link of that video. I have used a virtual laboratory developed by IIT Roorkee. By following that video and the resources available on the virtual laboratory platform developed by IIT Roorkee, you shall able to experimentally feel that comparator circuits. So with this, thank you for attending this class.